This assessment asks us to explain why the reaction shown on screen results in a racemic mixture. Now, even if this is a reaction that we haven't studied before, what we notice is that this carbonyl is a planar functional group, and it's reacting with this negatively charged methyl group. With a planar functional group, when that reaction happens using the arrows as shown, approach can happen from the front or from the back. And because it's a planar object, approach from the front and the back are going to be equal. Let's say a little bit more about that. What I've done here is I've taken and abbreviated it, taken this carbonyl and turned it on its side, where now we have the phenyl group coming away from you and the alkyl group coming towards you. And what this A here is meant to show is attack from the top, the nucleophile attacking from the top of this planar ketone. Over here, down here, we have the opposite, approach from the bottom. And I've specifically drawn approach from the top and approach from the bottom in a way that this dashed line here represents a mirror plane. And what you notice is that A and B are mirror images. And I'll go ahead and tell you, they are superimposable mirror images. So if we think of A and B as being the transition state of the two possible reactions, approach from the top and approach from the bottom, then what we see is that the two transition states are enantiomers of each other. What do we know about enantiomers? They're going to be identical energy, and that's going to be the case for transition states as well. So if we come over here to our reaction coordinate diagram, this one's going to be a little bit different because it's going to be a reaction coordinate diagram that goes right and left. So the possibility is that the nucleophile can add from the top to go in the direction of A, and it's going to have some activation energy. Or it can go in the other direction, approach from the bottom, we'll call B, and it's going to get, I'm going to try to keep these lines as close to the same height as possible, because that's how they would be. So this would be B, and the activation energy that leads to B would be the same. Now, how do we know that? Again, because the two transition states are enantiomers of each other, those transition state energies are going to be the same. Because they both start at the same spot, the activation energy is going to be the same. And if the activation energies are the same, then the rate of formation is the same. And so we would end up with an equal mixture of B and A because neither activation energy is lower than the other. Why? Because the transition states are enantiomers.